Okay, let's finish off this chapter strong. Finally, intersecting planes. Section K, let's go. First, I want to just recap some things we know about simpler situations. So, when we have two lines and they are interacting in a two-dimensional situation, so two lines in a plane, they might either intersect, and if they do, that intersection will be a point, or they might be parallel to each other, or they might be coincident. If we have two lines in three dimensions, they might intersect, again, in a point. They might be parallel, they might be coincident, or a new word here, they might be skew. If we have two planes in three dimensions, we also have three things that could happen. We've got images of them down below here. They might intersect, but in this case now, the intersection of the two planes will be a line, or they might be parallel, or they might be coincident. And what we're going to talk about in just a minute is if we have three planes in three dimensions, how could they interact with each other? And it turns out there's 8 different ways that could happen. We'll see images in just a moment. But before we move on, there are some interesting questions I think that could be asked as natural extensions of this particular table. For example, what if we took this to the next dimension and we had two three-dimensional spaces interacting with each other in 4 dimensions? So that's the extension of having two lines in 2 dimensions or two planes in 3 dimensions. So the dimension number is always one more than the dimension of the construction. A line is one-dimensional, so here we're talking 2 dimensions. A plane is 2-dimensional, so here we're talking 3 dimensions. If I had a 3 space in 4 dimensions, it turns out they could also interact in 3 different ways. Their intersection would be a plane, or they could be parallel, or they could be coincident. Don't try to visualize this. You will almost certainly fail, but understand that by analogy, this has to be true. And if you go on to study further linear algebra, you can do all sorts of fun stuff with null spaces and whatnot. This is a very elementary result there, but the first time you think about it in terms of geometry, this is pretty neat stuff here. What if we had 3 lines interacting in 3 dimensions? Up here, we went from 2 planes to 3 planes. Well, what if we went from 2 lines to 3 lines? And for that, I've found 13 ways. I am not sure if I've missed any, but I don't know. From there, could there be a pattern? So we had 2 lines in 2 dimensions, 2 lines in 3 dimensions, 3 lines in 3 dimensions. What if we had 2 lines in any generic n dimension? Would there be a pattern to predict how many different ways they could interact? What would the number be? If there were n lines in n dimensions, is there a pattern to predict how many ways they could interact? And so on. We could bump, we could bump the dimensions of the constructions up. We could bump the number of how many of constructions we have interacting with each other up. And we could bump up the dimension that is our little sandbox that we're playing in up. And I don't know. There's a lot of open questions here that I don't have answers for, but perhaps I've piqued your interest. Anyhow, back to the topic at hand. 3 planes in 3 dimensions. I said there's 8 possible ways they can interact, and here they are. Let's go through these one at a time and also make a note of what the solution set might be. So in the first situation, we have all 3 of the planes are just coincident with each other. So in that case, there are infinitely many solutions, and those infinitely many solutions take the form of a plane. In the second set, we have 2 planes which happen to be coincident. So P1 is equal to P2, but they intersect P3 in a line. So there are, again, infinitely many solutions, but in this case, those solutions are a line. In example 3, 2 planes are the same, but the third one is parallel to those first 2. Here, there are no solutions because we're looking for a set of points which are common to all three planes. So there are no such points if two of the planes are parallel. And that is the case as well in example 4. There are certainly places where the first and the second plane intersect in a line, and the second and the third intersect in a line, but the first and the third are parallel, so there's no general solution there. Clearly in example 5, all three of the planes are parallel to each other, so there's no solution there. 6, this is the exciting one. They all meet in one single point, so there is a single, unique is going to be the word we use, solution. In situation 7, there are again going to be infinitely many solutions here. They're all meeting in a line. And in 8, there is, again, no solution. I don't really know why the book ordered these in the way that it did. There seems to be no rationale to this. But anyhow, there are, 3 situations with infinitely many solutions, 4 situations with no solution, and 1 situation with a unique solution. When we are solving the problems we're about to look at, we'll be asked to first to find a solution if it exists, and then often to give a geometric interpretation of it. So if there are no solutions, we need to be able to analyze the algebra we have in front of us and deduce, well, which no solution situation is it? If there are infinitely many, which of the infinitely many situations are we looking at? I'm not going to go through an example of each one of these because a lot of the work is all the same stuff. I think it'll make sense by the time we get through a few of them. I'm certainly not going to do an example of the first one because, as you'll see, the problems we're going to be looking at are just solving systems of 3 equations with 3 variables, and we're only going to have this first situation if all 3 of the equations are the same. And I can promise you, you won't have something so simple in this setting, so I'm not going to waste any time on it. All right, let's look at some. So there's 6 in front of us here. I'm not going to do all of them, and I will be skipping over quite a few of the easy steps, but let's hit the main points. So our plan of attack here is to use the elimination method for solving a system. We're going to choose to eliminate one variable from 2 different pairs of equations. I'll show you what I mean. So in letter A, I'm gonna choose to eliminate the variable y because I see that I can eliminate y very easily from different pairs of these. Specifically, if I take the first 2 equations and eliminate the y, I can add them together, so it's going to give me 2x plus z is equal to 6. If I then take the second and the third equations and I add them together, that'll give me 5x minus 3z is equal to -7. And if I then solve those 2 equations, I'm going to get x equals 1 and z equals 4. Putting those back into any of the original 3, I'm going to get y equals -2. Since I've gotten a value for each of my 3 variables, this particular system represents 3 planes that are intersecting in a unique point. The point 1, -2, 4. Okay, letter B. I'll do the same thing. I think y is also the easiest one to eliminate in letter B. If I take the first 2 equations and I put them together, I will get 3x plus z is equal to 9. And if I take the second 2, well, I suppose I'm going to want to rewrite the second one there to be 4x plus 2y minus 2z is equal to 16. So really, I'll be taking those 2 together. Regardless, that's going to give me 9x plus 3z is equal to 27. And then look at those 2 equations. They have infinitely many solutions. The blue one is just 3 times the red one. So that means that my planes are going to have infinitely many solutions. The question now is, do they intersect in a line, or are they all coincident? Well, I promise you they wouldn't all be coincident. And these 3 planes are definitely not all coincident. Just look at their normal vectors. Their normal vectors are not the same, nor are they scalar multiples of one another. So we would just write these three planes intersect in a common line. But now the question is, what is that common line? And this is not as bad as it sounds. I referenced this in a prior video. Let's just take one of the simplified lines that we had just ended up with. So we had 3x plus z is equal to 9. What we're going to do is we want to introduce a parameter, right? Because the way we're going to write lines is going to be with some sort of a parameter, whether you want to use lambda or t, I don't care, or any other letter, whatever. So we're going to pick either one of these variables, either x or z. Z is, I think, easier in this case, but whatever. So I'm going to say z is equal to lambda. If z is equal to lambda, then x must be equal to 9 minus lambda divided by 3. Okay, that should seem fairly obvious. And then I substitute both of those values back into one of my originals. It really doesn't matter which one. And I solve for y, and we're going to get y is equal to 5t plus 6 divided by 3. And there you go. Those are your parametric equations for the line of intersection between those 3 points. You will often be asked to state the general solution, and that's what they're referring to, is something with a parameter. As I said, it doesn't matter whether you chose z equal to lambda or x equal to lambda, or if you had eliminated a different variable, you could have even set y equal to lambda. So there are 3 very different looking answers to this equation. I'm not going to take the time to work them all out, but that's something for you to be aware of if you are ever checking your work against a mark scheme or against a friend or against your teacher. If you choose a different variable to kind of become the parameter placeholder, then you're going to get a very different looking, but still correct answer. So letter D. Letter D very obviously has no solution, because if you look at the first 2 equations, the normal vectors are scalar multiples of each other. The coefficients of x, y, and z are just, in the second, are 2 times that of the first. And 11 is certainly not 2 times 8. So there's 2 parallel planes. That's it. There's no solution. But let's pretend I didn't see that. Let's proceed as normal. We're going to have to eliminate one variable from 2 pairs. If you choose the first 2 equations as one of your pairs of lines, then you're going to figure out right away, like as soon as you multiply the top equation by 2 to try to eliminate any of your variables, you'll see that they all go away, and you'll just have 0 on the left and a non-zero constant on the right. And that'll be your clue that there's no solution. But if you get really unlucky and you happen to choose, say, the first and the third I believe are going to get you 2x plus 2y is equal to 6. And if you choose the second and the third is going to get you 4x plus 9y is equal to 7. So then you're going to need to combine those 2, solve those 2, excuse me, and that's fine. Like, they have a solution. You're going to get x equals 4, and you're going to get y equals -1. But you need to substitute those back into all 3 of the initial equations. I hope I made that point clear in part A. Perhaps I didn't. When we solve the system in example A, you need to put the values of x and y back into all 3 of the original equations to make sure that you get the exact same third coordinate. Because, for example, here, if you plug in those 2 values into the original 3 equations, you will get c is equal to 3 for the first one. You'll get 1/2 for the second one, and then you'll get 3 again for the third one. So clearly, again, no solution, but what's the description that's happening here? Well, we have two parallel planes, the first and the second. And then since the third one is neither parallel nor coincident to either of the first, then the third plane is cutting through both of the other parallel planes. And the last one we'll look at is letter E. Letter E, again, very obviously has infinitely many solutions, because if you look at the first and the third, the third equation is clearly the first equation times 3. So right away, I would see that, and I could really answer this question doing almost no mathematics at all. But let's say I didn't see that. I'm really bad at looking for these shortcuts, so I choose the first two. Let's eliminate x this time. If I choose the first two, I'll get 2y minus 3z equals negative 3. Try that again. There we go. And if I choose the second and the third, I can get negative 6y plus 9z equals 9. And then I'm going to have to come face to face with the fact that those two equations are multiples of each other. So again, infinitely many solutions in this case. Now I need to find out, well, what kind of infinitely many solutions are there? So I just go back and I analyze the normal vectors. As I said, I noticed that these two are the exact same equation, so those two planes are coincident. Meanwhile, the third plane must be intersecting them, as its normal vector is not the same, nor is it a scalar multiple. So we have two coincident planes and a third plane simply intersecting them in a line. Once again now, we need to work out what is the equation of that line. So we can take one of the last equations that we had, 2y minus 3z equals negative 3. Again, choose your favorite variable here to serve as your parameter. Generally speaking, books and mark schemes seem to use z most often, so I'll just follow in that. So z is equal to lambda. In that case, y is going to be equal to negative 3 plus 3 lambda divided by 2. And x will be lambda plus 5 divided by 2. So there you have it. Those are your parametric equations for the line of intersection. But we absolutely must discuss what the calculator can do, because there will be problems like this on paper 2. So in all cases, we'll be going to menu, algebra, and then solving a system of linear equations. How many equations are there? There's 3. Once you click down, it automatically fills in that z should be the third variable. Very convenient, this calculator. We press OK. I'm just going to type the thing in as it appeared. Let's do the first example. We just type in the system exactly as it appeared in the question and hit enter, and lo and behold, we get an answer of 1, negative 2, 4, as we had in our work earlier. That's obvious. What's going to happen when we have no solution or infinitely many solutions? So this was the example B, and the answer that it spits out is something very curious. We have this number C1. That's the parameter. That's lambda. And this even matches the answer that that we got for this one. Our answer, we chose z equal to lambda. So our z coordinate here is the strange C1. Our y coordinate, we wrote it in a slightly different form. We wrote 5 lambda plus 6, all divided by 3. But that 6 over 3, that could have turned into just a plus 2. So that's the exact same thing, and the x value is also the same thing. So this literally tells you the parametric equations for the line of intersection. It's very cool. Of course, very conveniently, when there is no solution, it will tell you so. So everybody, please know how to use your technology appropriately. There have been plenty of examples on paper 2 in the past where you are expected to use this process. If you try to do it by hand, you get all these nasty fractions, and it's going to be very time consuming, and you'll be very likely to make a mistake. This process takes a few seconds. You need to know how to do this. Don't be that person who tries to solve it all out on pen and paper. Obviously, if you have a TID 4, there's another way to do this, but you're going to have to speak to me privately, and I can walk you through that. If you're using a Casio or an HP Prime, I don't know, Google it. I don't have enough experience with those calculators to help you, but so yeah, calculators are great, but they can't do everything. They won't be able to help us with this system, believe me. I tried, but it didn't know what I was asking it to do. But that's all right. We can do this by hand, no problem. We're going to approach it in the exact same way. First, I'm going to just look at these. Can I tell right off the bat that anything is parallel or coincident? No, because we have this m is floating around in two different equations, so I can't analyze anything for a shortcut. So we're going to eliminate a variable. I chose to eliminate y in my work. That seemed like an easy choice. Using the first and the third equations, you can rewrite that as 3x 3x minus 2 plus m z is equal to 7. And then using the second and third equations, you can get that down to m plus 1 times x plus m plus 1 times z is equal to 0. From there, we are going to try to solve this system. Notice from the blue equation that as long as m is not equal to -1, that would mean that x is equal to negative z, or I'll use z equal to -x. That means that as long as it's not equal to -1, then we can substitute this into the original green equation here, and then that would get me, excuse me, that should be a plus. I was about to have a panic moment. That'll get me 5 plus m. X is equal to 7, and then x will be equal to 7 divided by 5 plus m. And that's great. That means that I will have a solution as long as m is not equal to -5. So m being equal to -5 indicates that there will be no solution, because I can't divide by 0 here. So that's a huge red flag. Which one of the many no solution cases is it? So now if m was -5, we can then mentally fill that value in here, and now we can think about the normal vectors for all three of these. And we see that still none of them are parallel. So what we actually have is the case where we have three planes all intersecting each other, but in different places. So like that's a plane, and that's a plane. There's still no single point or points where all three of them intersect. For letter B, to show that there are infinitely many solutions for another value for m, well, we did mention there was this other special value over here when m was equal to -1. If m was equal to -1, then the blue equation would become 0 equals 0, and that's always true. So m equal to -1 is going to give us infinitely many solutions. And if we substitute that in here and here, you will notice that the second and third equations are now, they're the same. So those two planes are going to be coincident. One is just, the other one multiplied by -1. And the third one is just intersecting both of those coincident planes. All right. Letter C. For what values of m does the system have a unique solution? Well, it's like all the other values for m. So as long as m is not equal to -1 or -5, then there is a unique solution. Interpret that result geometrically. Three lines meet in a common point. And to show that that solution is going to be given by these values of m, well, look, I already figured out the x value in my prior work, and I am not going to write this all out, but if I were to take that value for x, 7 plus 5 over m, and then substitute it in right there, we could get this value for z, and if we took both of those and put them back into any of the other equations, we could get the required y value. So that's pretty much it for solving systems of equations with 3 variables and 3 unknowns. You're going to have to find general solutions. It involves introducing a parameter, This is a huge topic in linear algebra, as I've probably said a number of times at this point through these videos. But we're just kind of doing introductory examples with 3 equations and 3 unknowns, whereas linear algebra goes much bigger and has more advanced methods. On that topic, the textbook again references matrices heavily in this section, and I don't want you to worry about that unless you already know about matrices. As you can see from this video, you can solve any of the questions just fine by using normal old elimination methods. I should mention I kind of ignored a bunch of the vocabulary in this question. It said to reduce the system to a form in which the solutions can be determined. That's linear algebra speak. You won't see a question phrased like that on the IB. Whatever, even if you did, look, it's a system of equations. You should know what to do, right? As I've said before, if anybody wants a video on how to do this with matrices, I can put that together, but that is not particularly recommended. So hey, that's the end of chapter 15. We did it. Woo! I hope you've enjoyed my treatment of them. They're a really wonderful topic, and there's so much more to them. We've only begun to scratch the surface in this course. As I said, there's a little bit left for us to discuss in chapter 16, where we apply vectors to complex numbers, but it's all just 2-dimensional vectors and really basic stuff. But man, I really think this is a great topic. And as far as the IB exams are concerned, I would bet money that one of the longer questions at the end of the exam, so one of the section B questions, is likely to be a gigantic vector question worth somewhere from 10 to 15 marks. And if you don't have that question on paper 1, then I would bet twice as much money that it's going to be on paper 2. These are an extremely common question type for the end of the exam. So that's why we're going to be practicing in class quite a lot of, and have been practicing in class, quite a lot of those lengthy types so you can really get used to them. That's it for now. Keep studying, keep grinding, keep IBing, keep doing math.